Hey everyone, Mrs. Basega here, and today we're working on work again. Except this time, we're going to be working on the actual definition of work. So, you might recall that work is the application of force that moves an object through a distance. The actual equation for work is a little bit more complicated than just force and distance together. Yeah, those are part of it, but it also has this cosine theta term. The theta in this case will be the angle in degrees, so set your calculator to degrees. That's the angle between the force and distance. A helpful tool I'll encourage you to do, in addition to a free body diagram for this part, is draw what I'm going to call a force distance clock hands. Imagine your object is at the vertex of this triangle. Draw one arrow for distance and one arrow for force, and together those will be able to show you the angle you need for theta. So let's try an example. In example 1, a person pushes a box for a distance of 6 meters at 200 newtons of force. My force distance clock hands, the force is to the right, the distance is to the right, so the theta I need is 0 degrees. Force is 200 newtons times distance of 6 meters, and that's times cosine 0. Now, if you don't remember cosines off the top of your head, just substitute it into your calculator, making sure to always have your calculator in degrees. But cosine of 0 is always 1, so that's really 200 times 6, or positive 1,200 joules. And just to check, positive work means that it gains mechanical energy. This time, it's probably gaining kinetic energy. It gains energy because the force and distance are pointed in the same direction. Think of it as the person's force is helping it move faster. Since the force and distance are in the same direction, think of these two vectors as working together to add energy to the system. Let's try another one. So in example 2, a person lifts a 10 Newton box from the floor upward a distance of 1.5 meters. The person applies a normal force upward on the box, and the distance the box traveled is also upward. So I still have theta equals 0 degrees. Notice that a 10 Newton box means its weight is 10 newtons. I need to apply 10 newtons of normal force in order to lift it. So I'm putting in 10 for my normal force. D is going to be 1.5 for the distance traveled. Cosine of 0 degrees is going to be 1. So that's 10 times 1.5 times 1. Oh, let's make that look like a 15 there. Good. So again, positive work. This time I'm going to guess the positive work is adding gravitational potential energy to the system. Work positive, adding energy to the system. I wanted to show you this example because I wanted to show how force and distance don't have to be horizontal in order to have an angle of 0. As long as they're in the same direction, then the angle is 0 degrees, and I would be doing cosine of 0 in my equation. All right, example 3. Okay, so a person is carrying a 2-kilogram briefcase a distance of 100 meters across the street. According to the diagram, they're putting an applied force upwards, but notice that the force and distance are now at 90 degrees from each other, and cosine of 90 is always equal to 0. So if I go to FD cosine 90 degrees, that always gives me force times distance times 0. And anything times 0 is always 0. What that means is 0 joules of work are done. That means no energy is added to the system and no energy is taken out. So think of this person as going at constant velocity, keeping that suitcase at a constant height. Neither of those actions would change the energy of the system, so it makes sense to me that the work is 0. So with this cosine theta term, work has an angular dependence. So I want to elucidate that a little bit farther. So you already saw an example where if they're perpendicular, the force and the distance, perpendicular means that force isn't speeding up my object. It isn't moving it in the same direction. That means the work is zero. No energy is added to the system, and so there's no energy change. Now, if I have any acute angle, that means my force and distance are working together. If I have an angle anywhere from, let's say, 0 to 89 degrees, any acute angle, my force and distance are working together. My force is trying to speed up the object. So for acute angles, work comes out positive, and that adds energy to the system. Acute angles add energy. And that means the opposite is true as well. Obtuse angles means that the force is working in the opposite direction of motion. So imagine a Tobey Maguire Spider-Man trying to move the train to slow down. He's applying a force in the opposite direction of motion. Obtuse angles or opposite directions lose energy because they do negative work. At the end of a problem, you should always check and make sure that the angle you've drawn makes sense with the work you've calculated. If you were expecting positive work and got negative instead, double check that your calculator is in degrees. So let us try some angular examples then. If I have a problem that has multiple forces, in this case there are three, an applied force, a gravitational force, and a normal force, I probably want my first step to be drawing a free body diagram. In this case, my applied force is in the same direction as distance, that's acute angle, but my normal force and gravity are both perpendicular. It doesn't super matter what my normal force and gravity are because neither will contribute work. So let us do my force distance clock hands here. If the normal force is upwards but the distance is to the right, that's 90 degrees, that's perpendicular, zero work. If I do gravity versus distance, that's 90 degrees. So it doesn't matter that gravity is 49 newtons and 30 meters. If you substitute that into your calculator, cosine 90 gives you zero, so zero work. So that leaves only one force contributes work in this case. I would be doing the work for the applied force, so that would be 75 times 30 meters times cosine 25, and that gives positive 2039 joules. Grab a calculator because I don't do this in my head and you shouldn't either. Just to double check, positive work means that the system is gaining mechanical energy. Most likely, this system is gaining kinetic energy. Which brings me to my last example. What if I have a problem like this, where multiple forces do work? In this case, there's normal, friction, gravity, and applied force. But only two of those forces do work. As you can imagine, normal force and gravity are perpendicular to the distance. Those are not going to contribute work, but the applied force and the friction force will. The friction force acts at 180 degrees from the distance. So if you drew your force distance clock hands here, that's 180 degrees when I do cosine. So that gives 250 newtons times 7 meters times cosine 180. This gets me a negative amount of work, and that makes sense to me because friction should remove mechanical energy from the system. Similarly, when I do the positive work for the applied force, that will make sense because that is gaining mechanical energy, probably in the form of kinetic. So I do 450 times 7 times cosine 38 to get positive 2,482 joules. If I have multiple forces that do work, I simply add them together to see the net result. The net, or the total work in this case, is positive 732 joules, indicating that while the person was trying to speed the crate up and gain kinetic energy, the force was trying to slow it down by converting that kinetic energy over to heat, resulting in something that speeds up but less than one would predict. work is positive because kinetic energy is increasing. So it is about time to summarize here. Work is the application of a force that moves an object through a distance. You're going to draw free body diagrams in order to make sure you've identified correctly all the forces that are acting on your object. But then a new tool. Draw how each force interacts with a distance. We use this force distance clock hands here to find the correct angle to use in the force distance cosine theta equation. That's step 3. Finally, when you reach the end of a problem, double check to yourself, does it make sense that this force has done positive work? If it did positive work, is it gaining energy in the system? It should be. Negative work should lose energy, and if work is 0, that means that force does not change the energy of the system, and it could be that the total energy of the system is conserved. Righto. So give these problems a try. It is the last 2 pages of the homework. Best of luck.